Well, as you can see in this discussion, we're going to talk about functions that are called piecewise defined functions. And a piecewise function or a piecewise defined function is a function with two or more formulas for computing the value of y. Now, I need to add in here the formula use, that is, which formula we use, the formula to use, to compute y with, to use, depends on the value of x. So here's an example of a piecewise defined function. We'll say f of x is equal to, and then you'll see a brace, a curly parenthesis. It's called a brace. And then you'll see two or more lines. In this case, there's 3 lines. And each line is a formula. So it says to calculate y, we use the formula x minus 1. That is if x is less than or equal to negative 2. Now, if x isn't less than or equal to negative 2, we use a different formula. We use the formula 2x to calculate y with if x is between negative 2 and positive 2, but not including either negative 2 or positive 2. And if it doesn't satisfy either one of those conditions for x, then we use the formula x squared to calculate y. And we use that formula whenever we have an x value that is greater than or equal to 2. So we might have more than 3 rules. Usually it's 2 or 3, but we could have more. So this is an example of a piecewise defined function. Now, many times we're going to be asked to evaluate that function. So it might say evaluate or find the value of the following. Okay, find the value of the following. And so the first example might be we're asked to find f of 5. Well, the first thing we have to do is look up at the different formulas and see which condition the x value of 5 is. See, there's our x value. And so is our x less than or equal to negative 2? Or is our x between negative 2 and positive 2? Or is our x greater than or equal to 2? And our x is greater than or equal to 2 because our x is 5, isn't it? So that tells us we use the formula x squared. So we'll put a 5 in for x in the formula x squared, and we get 25. Now, on the other hand, if we were asked to calculate f of negative 3, we would see that the x value that we're using now satisfies the condition. Remember, that's the x value. And this x value satisfies the condition that x is less than negative 2. Well, if x is less than negative 2, we use the formula x minus 1. Okay, so if we're using the formula x minus 1, we put our negative 3 in for x and subtract 1, and so we get a negative 4 result. So we only use one formula for a given x. We don't use all 3 formulas or 2 formulas simultaneously. We use one single formula, and the value of x tells us which formula we have to use to calculate y with. Let's look at another example here. How about f of 0? No, let's do this. How about f of, whoops, my bad. How about f of 1/2? Well, remember, this is our x value. And now we look through the conditions. Is this true for x up here, or is this true for x, or is this true for x? And we notice that for our x of 1/2, our x of 1/2 is between -2 and +2. Remember, our x is 1/2. And so that's true. That means we use the middle formula to calculate with. So the middle formula is 2 times x, and since our x is 1/2, we have 2 times 1/2, and of course that value gives us 1. So the idea of calculating or evaluating for these piecewise defined functions is not a difficult task. We just have to get used to these. We see these a lot later on in other courses, these types of functions. The part that might be a little more challenging is if we're given a piecewise defined function and we are asked to graph it. And so we're going to consider that next, except we're going to take it in pieces. And first, I'm going to remind you of a few things, and then we'll get to the graphing of piecewise defined functions. First, I just want to remind you how we graph something like f of x is equal to 3. And so when we're graphing that, you know, we still kind of are translating in our mind that we're being asked to graph y equal 3, and we recognize that that's a line we're graphing, okay? And it's a horizontal line, isn't it? And it's a horizontal line where y is always equal to 3. So if we were to look at the graph, and we imagined here's y equal 1, here's y equal 2, here's y equal 3. 1, 2, 3. And of course, these x values are not as critical for us right now in this graph. So the line, graphing f of x equal 3 is nothing more than the horizontal line that goes through the y value of 3. So that's the graph that we've drawn right there. Now, secondly, I know we know how to do this, but I'm building to something. We're asked to graph maybe g of x is equal to 2x minus 1. G of x is equal to 2x minus 1. Now, we happen to know in this case that we have a line, okay? And so we would begin to set up to graph that line. And again, we're thinking, oh, I'm going to graph this. I'm thinking of graphing y is equal to 2x minus 1. That's the way I think about it. So I set up my coordinate axes, okay? And, let's say something like this. I'm just sketching this in is not that big a deal. So we scale the y-axis a bit, okay? And so this is, of course, where -2 is. This is -1. This is +1, +2, +3. And then, of course, along here we scale as well. Okay, so here's a 1, and here's a 2, and here's a 3, and here's a 4, and so on. -1. Okay, and so I just plot some points. And I'm going to do this in my head. I'm going to let x be 0, and y is -1, so that's this point. And I'm going to let x be 1, and so y would be 2 minus 1, which would be 1, and so that's this point. And if I let x be 2, I get 4 minus 1, or 3 for y, and that's this point. And so we would have a line that went like this, wouldn't we? Okay, no big deal. Now, I'm going to change things a bit, because in the graph that we just did, we understood that we could use any x value. And in that case, we say the domain is implicit. That since there wasn't anything told to us other than what we saw, we were assuming we could use any x value at all for the domain because there were no restrictions. But now I'm saying graph g of x equal 2x minus 1, comma, x is greater than or equal to 0. Now this is a different issue. It's telling us here that we can't use just any x we want. We can only use x's that are 0 or positive, since we can't use all x's. So that means we're going to have a line, if you will, but we're not going to have an entire line since we can't use all x values. So let's kind of set this up again, as we did a moment ago. course, here's where negative 1 is for y, negative 2, positive 1, positive 2, positive 3, a 1, a 2, a 3, and so on. We can continue. But now if I'm making a solutions table here, see, I can't choose an x that's negative 1. I've got to rule that out. But I can choose an x that's 0. Because it says x can be any number that is greater than or equal to 0. So I can choose x to be 0, and when I do, I get a y of negative 1. So this point is on the graph, but that x value of 0 is the very first x value I can use. I can't use any x's that are on this side, can I? Okay? And so from there, I could continue. I could say, oh, well, let's choose x to be 1. And when we do, we would get a y of 1. And let's say we could say, let's choose x to be 2. And when we do, we would get a y of 3. So it sounds like what we just did a moment ago, except that this time the line is not really an entire line, it's an array, because we can only use x's that are 0 or positive. And so that's what I've seen. It's not an entire line. That's an important concept when we're dealing with piecewise defined functions, okay, although that's not what we have yet. Okay, let's graph one more here. Let's graph h of x, which is equal to, let's say negative x plus 3. And here we have the condition, though, that x has to be less than 2. Okay. Okay, so let's set this up, and let's see here. Let me do something like this. Here's the x-axis. Here's the y-axis. 1, 2, 3, 4, and so on. 1, 2, 3, 4. There's 5. Now here maybe a 1 and a 2 and a 3 and a 4, and over here a negative 1 and a negative 2, and so on. Okay? Negative 1 and negative 2, and so on. Now, notice here we can only use x's that are less than 2. Now this isn't really part of the graph, but what I'm going to do is I'm going to find out where x is 2. And I'm going to draw a vertical dashed line through it. Now, the idea here for me is this is a guideline. And since I can only use x's that are smaller than 2, my entire graph is going to lie to the left of that vertical line, because to the right of that vertical line are x values that are bigger than 2. Okay. So then I go in here and I start thinking, okay, well, let's plot some points, because I recognize that what I'm graphing is y is equal to negative x plus 3, which is going to be a line, but not a whole line. Okay. Now, I ask this question, could I choose x to be 2? Well, no, x has to be less than 2. Could I choose x to be 1? Oh, I could, because 1 is less than 2. And if I choose x to be 1, I think I'll get a y value of 2. And so I can plot that point. That'll be right here. Okay. Can I choose x to be 0? Well, sure, because 0 is less than 2. And so when I put a 0 in for x, I get a y value of 3. So that's this point right here. Now, could I choose x to be negative 1? Sure, because negative 1 is less than 2. Now, here I have to be a little bit careful, because when I put a negative 1 in for x, remember I have the opposite of x. So I have the opposite of negative 1, which is 1, plus 3, which will give me a 4. So when x is negative 1, my y is actually 4. Now we know we have a line, and so we have, but it's a partial line. So we have a line that looks kind of like this. Okay. Now here's the mistake that most students make. They stop it right there, and you know the kind of the question is, well, what's the first number I can use that's less than 2? And see, the first number I chose to use was a 1, but 1.5 is less than 2, And 1.9 is less than 2, isn't it? There are a lot of numbers less than 2. See, I haven't considered any of the numbers that are between 1 and 2 at all. And I've left out that part of the graph. So here's the way I handle this. I'm not allowed to use 2 because x has to be less than 2. But suppose I did. Suppose I used 2. And I calculated the y, I'd get negative 2 plus 3, or I'd get a 1. So 2 comma 1, if I could use 2, would be on the graph. Where is 2 comma 1? Well, it's right there. Okay. But since I can't use 2, that point won't be there. But all of the points on the line right up to that position will be there. See, I've filled in the rest of the graph. I just can't use that one value of x that is 2. And so my graph at this end, since 2 is not allowed, would be an open dot instead of a solid dot like we had above. Okay. Well, on the next page, let's actually graph a piecewise defined function, and maybe we'll graph more than one, but let's certainly start with graphing 1. Okay, in this case, our function that we're to graph is the piecewise function f of x is equal to 2x plus 4 as long as x is less than 1, and it's 4 minus x as long as x is greater than or equal to 1. And notice this in the future. There's usually a breaking point in the piecewise defined function. See, on one side of an x value, we use one formula. On the other side, we use a different formula. And usually one will have an equal portion to it and the other will not. We can't have both have equal portions to it because that would tell us that we have 2 different ways to calculate y, and that could give us 2 different values of y for one single value of x. So one will have a non-equal part and the other will have an equal part. Now, here's the way I go about this. I first set up my graphing, my coordinate axes. And, I'm not really sure what kinds of values I'm going to get. And so I have to be a little bit careful. But let's do this. Let me pause and get these set up. Okay, I've set up a coordinate axes. And in this case, we're making each tick mark 1 unit. So here's 1, 2, 3, 4, and so on. And of course, down here's a negative 1, negative 2, negative 3, and so on. And across here, of course, there's 1, 2, 3, 4, 5, and negative 1, negative 2, negative 3, negative 4. I know those are fairly small. Now, here's what I end up doing. I say, look where the break is x is less than 1 and x is greater than or equal to 1. So I imagine, whether I draw it in here or not, a vertical line through the x value 1. It's dashed. Now, what I do know is on one side of that vertical line, the graph is going to look one way, and on the other side, it's going to look a different way because we have 2 different formulas. So whenever I'm on the left of 1, that is when x is less than 1, I use the formula y equal to x plus 4 to calculate y with. And I know that that will be part of a line because y equal to x plus 4 is a line, but I'm only using x's that are less than 1. So what kind of x's are less than 1? Well, I can't use 1, but I could use 0, I could use negative 1, I could use negative 2, and so on. If I use 0, then I'll get a y value of 4. If I use negative 1, then my y value will be positive 2, won't it? 2 times negative 1 plus 4. And if I use a x value, of negative 2, then my y value will be 0. So when I start plotting these points, 0, 4, okay, negative 1, 2, negative 2, 0, we get the idea that we have part of a line. See, we see this much of the line, okay? It goes like that. But I'm missing all of the x values between 0 and 1. And so like I did before, although I'm not allowed to use 1, if I did, I would calculate my x value to be 6. Excuse me, my y value to be 6. So if I were allowed to use 1 for x, my y value would be 6, and that would be this position on the graph. But since that position, that x value is not allowed, since 1's not allowed, that point's not really on this part of the graph. And so, but right up to that point is on the graph. So I'd have an open dot on that part of the line. Okay. Now, when I am having x's that are greater than or equal to 1, then I use the formula y equal 4 minus x to calculate my y's with. And I know that that will be a line, although part of a line, since I'm only using x's greater than or equal to 1. Now in this case, 1 is allowed because x can be greater than or equal to 1. And so when I choose x to be 1, my y calculates to 3. And I could choose x to be 2, and my y would calculate to 2. And if I used x to be 3, my y would calculate to be 1. And so I just go and plot these points, 1, 3, but this time that point is on the line. So I fill it in. And 2, 2 would be here, and 3, 1 would be here. And so this part of the graph looks like this, where we have a closed dot. Now, while we're doing this, notice that this is the graph of a function, although I called it a function to begin with. If we employ the vertical line test, see, a vertical line here crosses the graph only once, and a vertical line here crosses the graph only once. The only suspect place is at the ends of each of these pieces. And the vertical line there is the vertical line through x equal 1. And it crosses the graph at this point here, but since the point up here with that open dot is not really on the graph, then it's not crossing the graph there. It's going through a place where the graph is not. And so it, once again, the vertical line only touches the graph one time. And so this is in fact the graph of a function. Well, let's do another example, and we'll do that on the next page. I tell you what, before we do that, let me just make a point here. What if we would have had, because occasionally this happens, what if we would have had 2x plus 2 rather than 2x. Let's see, let me stop and think about this here just a moment. Well, let's say 2x plus 4 if x is less than 1. But let's say 6 minus x. No, let's say 7 minus x. 7 minus x if x is greater than or equal to 1. Okay, so I've changed it just a bit. Okay, that's all. I've changed it just a bit. And so let's think about what this graph would look like. I'm going to do this a little more roughly. 1, 2, 3, 4, 5, 6. Okay, this is where 6 is. And we'll say 1, 2. And so when we graphed this before, whoops. Man, I blew that. I apologize. When we graphed this before, this is where 1 is. Okay. Ignore that dot I made. We had an open dot here, didn't we? And then the graph came down and did something like this. Okay. Just imagine that we went through all the process. And so that was for x is less than 1, and we graphed y is equal to 2x plus 4, just like before. Okay. Now, on the other hand, when we have x is greater than or equal to 1, we would be graphing y is equal to 7 minus x. Okay. And when we start filling in here, we're going to have different values because the formula is a bit different, isn't it? But we can choose an x value of 1, and if we do, we get y is 7 minus 1, or 6. And we can choose an x value of 2, and when we do, we get y as 7 minus 2, which is 5. And we could choose x to be 3, and in this case, we would get y is equal to 4, wouldn't we? And so when we start plotting those points, okay. Now when x is 1, y is 6. That's that position right there. Now when we graph the left part of this, that is the 2x plus 4 for x less than or equal to 1, that hole was there. But when we go back and graph this time, when x is 1, y is 6, and so we actually have that point on the graph based on the second part of the function, 7 minus x whenever x is greater than or equal to 1. So on the one hand, we left it open, but on the other hand, we fill it in because we found out later that that point was on the graph. And 2 comma 5 would be right here, and 3 comma 4 would be right here. And when we drew this, then it would be a graph that looks something like that. Okay, so in this case, the two parts of the graph are actually connected rather than disconnected like they are above. And once in a while, we see that situation happen. Okay, now for, on the next page, a brand new function unrelated to these two. Okay, in this case, we're asked to graph a piecewise defined function that actually has 3 pieces. And you can see the bottom piece is actually constant, doesn't involve x at all. So we're going to approach this in a similar fashion to what we did a moment ago. And let me come down here and create this situation. Let's see if I can draw. Okay, I've drawn coordinate axes here. And again, each of these is 1 unit. So there's a 1, a 2, a 3, a 4, a 5, a negative 1, a negative 2, a negative 3, a negative 4, a negative 5, a 1, 2, 3, 4, 5, negative 1, negative 2, negative 3, negative 4, and so on. Okay. So now look where my breaks are. When x is less than negative 2, and then negative 2 to positive 2. So negative 2 is important, and so I'm just thinking, whoops, not real straight there, but I'm thinking at x equal negative 2, something changes. And then x is between negative 2 and positive 2, and then greater than 2. So at positive 2, I have another change. So there's actually going to be 3 different branches to this graph. There's going to be to the far left, there's going to be in the middle, and there's going to be to the far right. And so I start thinking about the values for x less than or equal to negative 2. And there I use the formula y equal x minus 1, which again I recognize as going to be a line, but although just part of a line. Now in this case, I can use negative 2 because x's are less than or equal to negative 2. So when I use negative 2, I calculate y to be negative 2 minus 1. And negative 3 would be all right, and y would be negative 4. And negative 4 would be all right, and y would be negative 5. So as I plot these, negative 2 comma negative 3 is actually this point, isn't it? And that point's actually on the graph. If I can read 1, 2, 3, negative 3. And when x is negative 3, y is negative 4, and so that actually ends up being this position, okay? And when x is negative 4, y is negative 5, and I believe that's this position, okay? And so this part of the graph looks this way, okay? Now, for the values of x between negative 2 and positive 2, then the formula, the equation, is y equal to x. And so I just start plotting some points here. Now, I'm going to notice that it's all right to use negative 1, it's all right to use 0, and it's all right to use positive 1. it's not all right to use -2, but I need to see where the graph is headed. And it's not all right to use +2, but I need to see where the graph is headed. So if I use -2, my y value would be -4, but that point's not really on the graph. Okay, so under those circumstances, -2, -4 is this position, but that point's not on the graph, so I have an open dot. Okay? Now, -1 I can use, and when I calculate y, I get -2. And so that's actually this position that is on the graph. And when I use x to be 0, I calculate y to be 0, and that's on the graph, and that's this position right here. And when I choose x to be 1, y is 2 times x, or 2 times 1, and so I'd get a y value of 2, and that's this position on the graph. Now, I'm not allowed to use x value of 2, because x has to be less than 2, but if I did, my y would calculate to be 2 times 2, or 4. And the point 2, 4 is this point, but that point's not on the graph. And so what we see is it goes right up to that point, and it goes right up to this point, but it doesn't include those points. So we have open dots on each side of this little line segment. And then finally, for x greater than or equal to 2, I'm graphing y equal 4. Remember, that's a horizontal line. But it's not an entire horizontal line. It's not an entire horizontal line because we're not using all x values. Now we can use the x value of 2 and y would be 4. And we can use the x value of 3, but y would be 4. Now 2, 4, kind of like what happened a while ago. In the middle part of the graph, that point's not there. But when we come to look at this right-hand side of the graph, that point is there. And of course, 3, 4 is there, and 4, 4 is there. We get a horizontal line that starts at x equal 2 and goes to the right because we can use any x's bigger than 2. So in this case, that's what our graph would look like. Kind of strange looking, isn't it? We have 3 different pieces, and it's because we had 3 different formulas. Well, I think that's all for this discussion on graphing piecewise defined functions. I know you'll do well on your homework. Good luck to you.